Hey students, thought I'd make another video solution. I got a couple questions from a magenta one, so it's a harder one here. It's number 64, chapter 26. I didn't print out the problem this time, so I'm just going to kind of draw a picture here. But it has what we might call a twin lead set of wires, and that would be two wires that are next to each other. And they have a radius, usually a pretty small radius, and they're identical, so I'll call this radius of r. And then they're often separated, and of course it depends how you measure them, but usually we measure around things from their centers, and so they say distance of d. In fact, the problem reads like this. It says, consider two long parallel oppositely charged wires of radius little r, with their centers separated by a distance d, which is much greater than r. So they're going to say d is greater than r. And the fact that they said it was much greater probably also means they're going to do a little bit of an approximation here. In other words, the surface to surface is probably roughly the same as center to center. And I think that's what they're going to imply here. Also, this is an important one because assuming that the charge distribution is uniformly on the surface. Now, I doubt if that would be true. If this was a top view here and we were looking at this top wire and this bottom wire here, one wire would get positively charged and the other would get negative, and we would have kind of this dipole effect. And that's if you remember this dipole picture, that's if the charges remained uniformly spread out. Chances are, though, the negatives would be drawn over and you'd have kind of a higher concentration here and just a few back on that side. And that's because this one here, lacking the electrons, because they were transferred over to here, means the missing electrons are probably a little more on that surface. So I'm quite sure there would be some kind of change in pattern to the electric field than the simple kind of the dipole that we talked about in chapter 23, and also for that matter in chapter 24, and that's what we're going to do, because again, I'll read it. It says, assume that the charge distribution remains uniform. So we can assume this is the same as a uniform charge distribution, and it makes this nice, perfect dipole. Again, you might call this a first-order magnitude calculation, because I'm sure that's not right, but we'll say it's roughly right. Just like we'll say the distance from the surface to the other surface is really a capital D minus 2r. But again, I think from a kind of a practical or engineering perspective, they're going to say, don't worry about that. Just, call it D or so. All right. So that's kind of where I'm headed with here, and I think that's why this is a kind of a magenta problem, even though when it says what's the capacitance, and so C, which is charge over the voltage, really isn't the hard part of this problem. This is what's new for this chapter, but when we have these charged wires, we worked out their electric field and their voltage in previous chapters. So maybe I'll just go back 2 chapters. You might remember, and maybe I'll do kind of a rough sketch. Where's my green here? I'll do a Gaussian surface in green this time. But if you kind of remember 2 chapters ago, we would do something like the integral of E dot dr equals charge inside over epsilon naught. And then we would look at this Gaussian surface. We would argue that the electric field is the same everywhere on the surface. Then we would go around the surface, so it'd be 2 pi r, and then we'd make some surface of length L. We would argue that the top and the bottom, the angle would be 90 degrees, and so we can forget about the top and the bottom as we do our closed surface. But on the round part, the face part, the angle would be 0. And of course, then the charge inside would be the linear charge density times the length. And when it was all said and done, and I know that was kind of a quick demonstration because I really think that the author intends for you to start right here. Knowing the electric field from one uniformly distributed charge, we can then get it for 2. We can then integrate that to get the change in voltage. So this is just a chapter ago, and so I'll do this. So here's the integral. And so if we integrate this, we can get the change in voltage, and then we can use that here and eventually get the capacitance. So I'm going to do this. I'm going to say, let's take a look then at the equation for the electric field, and this would be the electric field from just one wire. And so let's imagine the second one's not even there, and let's just say we're doing an integration starting at some distance from the center. And by the way, notice how this equation is written from the center. So if I go and say, what's the change in voltage? I would do an integral, and I would have to have the electric field, and then this dr would have to be some path that I choose. And let's pick an easy path. An easy path would be just kind of straight out. So we would go from R out to here, which I guess would be a D minus an R. It's also the direction of the electric field. That's kind of my orange color for my electric field. And I point that out because this says we can get the voltage, we can pick any direction, and we've got the field, and we just need to know the angle between them. And so I guess I would always encourage you to pick the easy path. And in this case, the easy path would be radially outward, so I could put cosine of 0 degrees. So I'm just going to go straight along this path. And of course, I'm going to also use the equation for the electric field, the 1 over 2 pi epsilon naught, and then the linear charge density over the radius, and then the dr. But of course, I picked this path because it is at an angle of 0. Or coming back to this picture, you might say, what I'm really doing is picking right across the center line. If I followed a path that was along the electric field on one of these bowed parts, I should get the same thing. But that would be a hard path to do and a hard integral to do. So let me not pick that one or pick this one. I guess technically this path would work too. I could start in the center and go across here and here and there. But again, that would be so incredibly hard to do. So pick a path, pick any path, pick the easy path. And so the easy path is right here. I can see the field, and that way the direction of the path I pick and the direction of the field are one and the same, just straight across. So I know the distance, I know the angle, and that's the easy one to do. Any of the other ones, I don't think we even know enough information to do them. I guess we could kind of go back and reanalyze our dipole and figure out what the equation is for this path. And I think it comes out to be part of an ellipse. Might be a hyperbolic ellipse, but anyways, we could figure all that out, but that's just killer amount of math and not necessary when we know a path that's really simple. So pick the simple one. So again, that's why I'm going to use that equation. That's why I'm going to put a cosine of 0 degrees, because I'm picking a path. I'm picking an easy path. I'm picking in the direction of the field, and I'm picking a path that goes right from the surface of this wire to the surface of that wire. And that's what all that means. And so the integral is actually pretty easy itself. The hard part is what I'm doing now, and that's explaining of why I pick that particular path. Now let me put the limits. As we said, we have to go from R to D minus R. And again, you might be tempted to say, well, I'll just call this the origin and go from 0 to D minus 2R, but that's going to get you in trouble because you're using an equation that is based upon the center. And so you can't all of a sudden change your 0 mark and still use the same equation, you know. Maybe like, I don't know, a silly example might be, all right, I'm going to take and have the equation for an easy line, y equals mx or something. And then I'm going to change my origin. I'm going to put it down here now. Well, now your equation for that line becomes mx plus b. It's something different because you got a different origin. So you would have to adjust your equation when you adjust your origin. And so if I have this equation for the origin being 0, if I want to change it to here, I got to adjust this equation, which then I could just do like an R. I could do like, you know, an R minus an R naught or something. So I guess it wouldn't be too hard of an adjustment, sort of like this one, but I just make sure I do it. But let me not do it because I think this is just a better way. Leave the equation the way it is. Leave the origin where it is, and therefore you go from R to D minus R. Now, I suppose one more thing I should say is I'm going to double this to get the change in voltage for both wires. Because remember, the dipole field is actually pretty complicated, but it technically is just the linear combination of these two fields. And so if you're going along this path, the combination when they're at an angle is much more complicated, but this one here, it's actually pretty easy. The electric field from the negative point inward and the electric field from the positive point outward. And so the combination of those two is just a doubling effect. Okay. And so you might basically say, I'm going to do an integral from here to here for one of them. Then I'm going to redo it for the other. And I suppose you might even say for the other one, I would go from here out to here. So I'd get the negative, but with the negative charge, I get the same value. So however you want to state it, it's going to come out to be twice as much. You just have twice the electric field. Okay. Now, technically, you have it at different spots because this field is strong here and this field is strong here. So it's not like it's double here of, you know, like the two we're adding together, like, you know, maybe you had twice the charge. So I don't mean that, but I do mean if you're going to add up over the whole thing, you've got a double here, a double there, and then that here can double with that one, and that one here can double with that one, and then as you move over, that one here would double with that one. And so there is a doubling going on, and so I'm just going to take advantage of that and say double it, even if it's at different physical locations. The total addition of all of them comes out to be doubling. And that might be hard to notice too. Anyway, so you can see I'm talking a lot here, just getting these few couple of lines, because now the easy part kicks in. So doing the integral is not the hard part. It's really kind of setting it up and justifying it, and then tying it together with past chapters, because I still haven't really even done this chapter. All right, so let's see. I guess I'll start by canceling off the 2's. Like all of my integrations, I might kind of look around for things that are constant, and so the pi and the permittivity of free space, lambda, and then I just have this integral of dr over r, which, as you know, is the natural log of r. And the limits are from r to a d minus an r. And if we take advantage of the properties of logarithms, this is the natural log of d minus r, and then minus the natural log of r. But taking advantage of the property of logarithms, when you subtract two natural logs, that's the same as taking the natural log of their quotient. And so I'll just write it in that fashion. Now, I might also do one more thing. Technically, this is the change in voltage. And of course, you can see I went with the field, and the field going from positive to negative is a decrease in potential, so it doesn't surprise me that this is a negative number. But when we do capacitance, we often say, what is the absolute value of the voltage between them? Because from one direction to the other is a negative, and then the other reverse of that is a positive. And so we kind of just by default know everybody understands one direction is positive, one direction is negative. We'll just use capacitance as an absolute value. So I really want the absolute value of the voltage between them. And so with that in mind, let me drop the negative. Also, kind of as I mentioned way at the beginning, they said D was much bigger than little r. So I'm going to say here this D minus R really is kind of the same thing as just going to D. So D minus an R, D plus an R, doesn't really change it by much. And so I suppose maybe better would put a little approximation symbols here. So now we can actually finish the problem, which says the capacitance is charge over the absolute value of the voltage difference. And maybe I should say approximately, because I'm going to use the approximate voltage difference. And it would be the approximate voltage, again, for two reasons. One, I have dropped this minus R, but one that we said at the beginning is we're going to assume that the charges remain evenly distributed, which, again, is probably more problematic than this, depending on how big those R's are. But again, if R is really small, then, again, you're saying these are more point charges and they don't get a chance to redistribute. So they're kind of saying one and the same. But let me go ahead and put this, and if it'll be okay, also while I'm putting it in for the lambda, I'm going to put Q over the length of this wire, the charge per length. And then I have this ln of D over R. And maybe just to keep it on one page, you'll see that the Q's cancel off. And this equivalent is to having the L down here. And then when you have something in the denominator of the denominator, you can flip it. And so those three, the L, the pi, and the epsilon go on top, and the natural log remains downstairs. And the final step is to move the L to the other side, because the question find the capacitance per length. So if you're buying this twin lead wire, it'll come rated at how much capacitance per meter. And so if you're going to, make an antenna or something and string this out, or some kind of communication or a ham radio, as you send these down to your antenna, maybe your antenna's on your roof if it's that close, or out in some back barn if you live on a big ranch, and so you're going to, maybe have 20, 30, 40, 50 meters of wire here. So you're going to want to know what the capacitance is per meter as you buy your electronics. And so that's how it would be labeled, as capacitance per meter. And it would be roughly equal to this calculation. And so based when the manufacturer, puts their twin lead together, they have a D, and then they have these R. They probably also factor in non-free space, because they're probably making one big plastic twin lead wire with kind of an elliptical shape here. And so it's not really free space. So we probably would have to multiply that by kappa, to be completely honest. And as long as I'm going along. But for this problem, we're done because this problem said show that it is equal to that. And so that's what would it be for free space. And the kappa would have to be thrown in there because, like I said, this would probably all be held together with a bunch of plastic and one big wire, and you buy a big spool so you can unroll it and hook up your radio and run the wire to your antenna. All right, well, hope that helps. Take care.